If someone asks you what an algorithm is, you probably think LeetCode, sorting, trees, graphs. Maybe you throw in neural networks and call it AI. But those two categories are just the tip of a much bigger iceberg. Beyond data structures and machine learning, there are at least 10 more distinct algorithmic fields, each with its own math, its own tools, and its own job market. Let's map the whole thing. First, cryptography. AES and Cha-Cha-20 keep your data secret. RSA and elliptic curves make SSL handshakes possible. And zero-knowledge proofs let you prove something is true without ever revealing why. This is the algorithms of trust. Next, distributed systems. When thousands of machines need to agree on one truth despite network failures, you reach for Raft, Paxos, or Byzantine fault tolerance. Kademlia routes peers in BitTorrent and Ethereum. And vector clocks keep events in order without any shared clock at all. Then there's numerical computing, the algorithms of continuous math, Gaussian elimination, QR decomposition, and the fast Fourier transform power everything from physics engines to JPEG compression to audio filtering. Randomized algorithms trade a small margin of error for massive gains in speed and memory. Bloom filters check set membership almost for free. Hyperlog counts billions of unique items using kilobytes. And Monte Carlo methods estimate answers no exact formula could compute in time. Quantum algorithms rewrite the rules entirely. Shor's algorithm factors huge numbers fast enough to threaten RSA itself. Grover's algorithm searches unsorted data with a quadratic speedup no classical computer can match. When a problem is too big for any exact algorithm, NP-hard, combinatorially explosive, metaheuristics step in. Genetic algorithms evolve solutions through mutation and selection. Simulated annealing cools its way out of bad local optima to land on a great one. Graphics and geometry algorithms render the world you see on screen. Bounding volume hierarchies and ray tracing simulate light. Delaunay triangulation and convex hulls describe shapes. Marching cubes turns raw data into a 3D mesh. And underneath all of it, operating system algorithms manage the machine itself. LRU and the clock algorithm decide what stays in cache. Round robin and the completely fair scheduler decide what runs next. Garbage collectors decide when memory gets reclaimed. That's 8 major fields. But push further into the specialized corners of computer science, and 4 more show up. Compression and information theory squeeze redundancy out of data. Huffman coding, the LZW behind your zip files, and Reed-Solomon codes that let a scratched CD or a damaged QR code still read perfectly. Control theory keeps physical systems stable. A PID controller holds your car's cruise control steady, and a drone hovering in place. Kalman filters fuse noisy GPS and sensor data into one confident estimate of where something actually is. Bioinformatics runs sequence alignment and genome assembly across multi-gigabyte strands of DNA, a specialized cousin of the string algorithms you already know from text search. In parallel, hardware-level algorithms, like prefix sum scans and VLSI routing, are built from the ground up to run across thousands of GPU threads or get baked directly into a chip. 12 distinct fields. So which one should you actually bet your career on? Let's rank them by jobs, growth, salary, and how much math they demand. By raw job count, traditional DSA and systems work still wins. It's foundational to nearly every engineering role. AI and machine learning comes second, distributed systems third, with graphics, security, and numerical computing filling out a solid middle tier. But growth potential flips the order. AI leads the next decade. Quantum computing carries the highest theoretical ceiling once fault-tolerant hardware arrives. And robotics-driven control theory is accelerating fast as AI moves into physical machines. At the very top of the pay scale, quantitative trading and AI research both stretch toward $800,000 a year at frontier labs and trading firms. Distributed systems and cryptography follow, with general application development sitting at the more modest bottom tier. And the math gets genuinely brutal at the top. Quantum computing demands linear algebra over complex Hilbert spaces. Cryptography leans on number theory and elliptic curves. Meanwhile, Traditional DSA asks for little more than discrete math and big O notation. LeetCode and AI aren't the whole map of computer science. They're just the two most visible neighborhoods. Somewhere in cryptography, distributed systems, quantum computing, or graphics is a field that matches exactly what you want to be good at. Pick the field that excites you, and go find out how deep it goes. If you want the next one broken down like this, subscribe.